When studying electricity, one electrical component that is of interest is a capacitor, and capacitance versus potential energy is often a misconception. And so to clarify, a capacitor is a device that is able to hold charge per an applied potential difference, or C equals Q over V. The energy stored within the capacitor is equal to the work done to charge it. And so in order to analyze this statement, we first must consider an experiment where we charge a capacitor. If we apply an EMF, an electromotive force, or an ideal voltage to an RC circuit, a circuit that contains both a resistor of some kind and a capacitor for storing charge, you'll see that as the circuit, as current flows through the circuit, the electromotive force on the capacitor will increase. However, it doesn't increase linearly. It increases exponentially with an asymptotic reaching of the ideal value near the top. This is because as charge is built up on the two parallel plates, you can imagine if I had two parallel plates, one positive and one negative, as we add negative charge to the negative plate, it becomes more and more and more difficult to add charge to the negative plate, thereby causing it more and more likely for this to asymptote off at the highest value being supplied in terms of potential difference, and also making it a non-linear increase as the energy is added to the circuit. So in order to properly calculate the work, something we first must do is we need to average the potentials being applied over the time in order to properly account for the difference from beginning to end. So therefore, if we think about the final voltage, VF, or the EMF in this case, minus the original, which in most cases would just be 0, averaged over those two values would be half. And so the voltage, the final voltage divided by 2 is the amount of potential necessary for the work. This is the potential difference that applies or stores the charge to the capacitor. And so in order to calculate the work, right, the work done to charge the system, then the work would be Q times the voltage. But in this case, it's important to note that the voltage is half. And so the work is Q times V divided by 2. Now, the definition of potential energy is the work necessary in order to get a system to a particular point. And so in this case, this is equal to the potential energy stored within the capacitor. Now, in most physics notation, at this point, we change from PE to capital U. And so capital U stands for the potential energy from here on out. This is mainly to avoid confusion with power and energy and electricity, electric field, etc., that utilize these letters. And so potential energy is given the symbol U and is essentially defined as 1/2 QV, as we see here. So the potential energy stored on a capacitor is equal to 1/2 the charge times the voltage. Now, if we recall at the beginning, here at the top I have the capacitance as being the charge per unit voltage. I can substitute that in for this Q here and redefine the potential energy stored within a capacitor as 1/2 CV squared. And so same formula with slightly different notation where we're utilizing the capacitance term. And so this is the potential energy stored in a capacitor.